Welcome students, I am Ravi Shankar. So today we are going to study about the Faraday's experiments. In our last class, I have given an introduction regarding the electromagnetic induction, where we have studied about the definition for magnetic flux. From the magnetic flux, we have obtained a relation for the magnetic flux both in uniform magnetic field as well as in non-uniform magnetic field that we have studied in the last video. In this video, we are going to study about the Faraday's experiment, from which how the electrical current can be induced. So what are these Faraday's experiments? More amount of explanation than that of writing in the board. Anyhow, let us see. When you are considering the Faraday's experiments, first of all, what Faraday considered was, he considered an thin insulated coil of wire. So, a thin insulated coil of wire having some n number of turns, and the two ends of the coil are connected to a galvanometer, the terminals of an galvanometer. So let us consider this as the galvanometer G, and let us consider this as the coil C. The purpose of the galvanometer, what is an galvanometer G? We can say G is a galvanometer, and with the help of this galvanometer, or galvanometer can be used to indicate the flow of electrical current. So we can say galvanometer is used to indicate the flow of electrical current. Indicate the flow of electrical current. See, initially, as there is no flow of electrical current through this coil of wire C, no deflection is available in the galvanometer. The needle in the galvanometer is at rest at its center position. Now, what you have to consider? You consider a bore magnet, which is kept nearer to that of this coil of wire. So I am taking a bore magnet, and if you are taking a bore magnet, the bore magnet is having north pole at one end and the south pole at the other end. So at one end you are having the north pole, and at the other end you are having the south pole. When you are placing the magnet nearer by that of the coil, then also you can see there is no deflection available in the galvanometer when the coil and the magnet are at rest. So the first observation that can be obtained from this experiment is, as long as, that we can take like this, as long as the magnet, and the coil are kept stationary, then there is no deflection. There is no deflection in the galvanometer. Indicating that no current is flowing through it, indicating that no flow of current in the coil, that we are considering it as the first point. Now what I am going to do, see, again I am taking this coil of wire whose ends are being connected to the galvanometer. Now what I am going to do is, the magnet that was being placed nearer to that of the coil of wire in such a way that the north pole of the magnet nearer to that of the coil C, and the south pole of the magnet is far away. This magnet is now moved towards that of the coil. when the magnet is moved towards that of the coil, you can see a momentary deflection available in the galvanometer. What do you mean by that momentary deflection? When you are moving that magnet towards the coil, the needle in the galvanometer produces a deflection and again it comes to zero. So second one, when you are taking the magnet towards that of the coil, so when the magnet is brought nearer to that of, brought nearer to that of the coil C, there is a momentary deflection. Momentary deflection means, what do you mean by that momentary deflection? Yeah, instantaneous deflection is being produced. After getting the deflection, the needle again comes to zero. So a momentary deflection is available or is produced. Momentary deflection is produced in the galvanometer, which indicates that there is a flow of what? There is a flow of electrical current. But after moving, if the magnet is kept stationary, then there is no deflection. Similarly, if the same bar magnet is moved away from that of the coil. So the third one, if the magnet is moved away, if the magnet is moved away from the coil C, what will happen? When the magnet is moved away from the coil, then also there is a momentary deflection available, but that the deflection is taken to be in opposite side direction to that of the previous case. That is, the direction of deflection when the north pole is moving in, if it is on the right hand side, then if the magnet is withdrawn, then the momentary deflection will be on the left hand side. So if the magnet is moved away from C, then we can say, then also there is what? Then also there is a deflection, and that deflection is a momentary deflection, but in opposite direction, to that of what? To that of the previous case. Okay, this is one experiment. Okay, what are the two conclusions? When the north pole of the bar magnet is brought nearer to that of the coil of wire, we can see a momentary deflection in the galvanometer on one side. If the magnet is kept stationary, after moving, if it is kept at rest, then there won't be any deflection. Similarly, the magnet which is being kept inside is taken out, is withdrawn out. Then also you can find a momentary deflection in the galvanometer. But now the momentary deflection in the galvanometer is just opposite to that of the previous case. That is, the direction opposite to that of the direction in which the magnet is moved towards. This is one set of experiment. Now, again, this experiment can be repeated. How? Instead of keeping the north pole nearer to that of the coil, you turn the magnet. See, you are having this coil here. The ends of the coil are connected to the galvanometer G. Now, when I am placing the magnet is placed in such a way that the nearer to the coil, you are having the south pole, and at the far end of the magnet is considered to be the north pole away from that of the coil C. Now also, when the magnet and the coil are kept stationary, there is no deflection. But at the same time, if the south pole of the magnet is brought nearer, then you can see a momentary, or you can observe a momentary deflection in the galvanometer, which is just opposite to that of the direction in which the deflection is taking place when the north pole is brought in. So opposite to that of the direction of deflection as in case of north pole. Similarly, when you are taking or withdrawing the magnet away, then the deflection will be just opposite to that of the previous case. So in this experiment, what are the two conclusions? Number one, when the south pole is brought nearer to coil, then also there is a momentary deflection. So in what direction? And the direction is opposite to the direction of deflection when the north pole is brought in. I hope you should have understood. See, when the south pole is brought nearer to that of the coil, there will be a momentary deflection in the galvanometer indicating that there is a flow of electrical current, but the direction of deflection is just opposite to that of the case when the north pole is brought nearer. Similarly, what is the second conclusion? You take this bar magnet away from that of the coil so that the south pole is moving away from the coil. Now you can write, when the south pole is moved away from the coil, what will happen? If it is moved away from the coil, then also there is a deflection in the galvanometer. There is a deflection. What deflection? There is a momentary deflection in the galvanometer, but in the direction, but in opposite direction to that of what? To that of the previous case. See, in both of the experiments, after moving, if the magnet or if the coil is kept stationary, then there won't be any deflection in the galvanometer. So from these two experiments, it was very clear that whenever there is a movement in the magnet towards or away from the coil, there is a momentary deflection, one thing. Then he repeated the experiment by keeping the magnet stationary and moving the coil towards and away. So the experiment can be repeated. How it can be repeated? Can be repeated by keeping magnet stationary. After keeping the magnet stationary, moving the coil towards or away, then also there is a momentary deflection. So momentary deflection. So what I can say, when the coil is moved towards that of the magnet, the momentary deflection will be on one side. If it is taken out, the momentary deflection will be on the other side. So from these experiments, what is the conclusion that was being arrived? The conclusion arrived was, see, what is the conclusion that you can able to get from this experiment? Conclusion arrived was, as long as there is a relative motion, in between, the coil and the magnet. What do you mean by this? As long as there is a relative motion in between the coil and magnet. See, with respect to magnet, the coil should move, or with respect to the coil, the magnet should move, or both can able to move. So if any one of either the magnet or the coil moves, or both of them are moving, then we are saying with respect to one another, both are in motion, or with respect to coil, magnet is in motion, or with respect to magnet, the coil is motion. So as long as there is a relative motion between the coil and magnet, there is a momentary deflection in the galvanometer. There is a momentary deflection in the galvanometer. So what it indicates, as long as there is a momentary deflection in the galvanometer, indicates that there is a flow of electrical current. Indicates that there is a flow of what? There is a flow of electrical current. There is a flow of electrical current where in the coil or in the coil of wire, which is indicated by the deflection in the galvanometer. This is the conclusion arrived. Now, by repeating the experiments, they found when will be the amount of deflection produced will be more. If the amount of deflection produced is more, then the flow of electrical current is also considered to be more. So the strength of the electrical current that is induced in the coil due to relative motion between the magnet and the coil increases, then the deflection also increases. So when that moment or when that deflection increases. So the experiment is repeated. The first one, the experiment is repeated by number one, having more number of turns. See, in the coil, if you are having some 100 or 150 turns, if you are increasing the number of turns to 200 or 250, then if you are moving it, then you can able to increase the amount of deflection. So by having more number of turns, we can able to increase the amount of deflection. Number two, then the experiment is repeated by moving the magnet faster. When the magnet is moved faster, either towards or away, then also the amount of deflection produced is high. Then third one, by increasing what? By increasing the strength of the magnet. See, the strength of the magnet, that is, another magnet can be taken with more power. That we are calling it out as the strength of the magnet. If the strength of the magnet is high, then also the amount of deflection is produced to get increased, which indicates that the amount of induced current is considered to be what? The amount of induced current is considered to be high. So these are the Faraday's experiment, with the help of which Faraday can able to state a definition. What is that definition? First of all, we will explain this. First of all, I have done what? I have given the experiment. See why there is a momentary deflection in the coil of wire when the magnet is brought nearer or when the magnet is brought away, or coil is brought nearer or coil is brought away from the magnet. This is one set of experiment. He has done another set of experiment also. See, in this experiment, by considering this experiment, one of the conclusion that I have arrived is, as long as there is a relative motion in between the coil and the magnet, there is a momentary deflection in the coil, indicating that there is a flow of electrical current. The amount of current induced can be increased, or the momentary deflection can be increased by repeating the experiment. It was found out that by having more number of turns, by moving the magnet faster or rapid. Then third one, by increasing the strength of the magnet. This is one of the experiments that was being done by whom? That was being done by Faraday. What is the second experiment done by Faraday? So let us go for the second experiment, which is done by the Faraday. See, what is the second experiment? He considered two coils of wire. So first of all, he considered one coil of wire, and this one coil of wire, let us represent it as P or primary. This primary coil of wire is connected to a battery, a key, and the other end of this battery through the key is connected to the other end of this coil P. And nearer to this coil P, they have considered another coil, and they are taking that another coil as a secondary. This coil generally considered to be primary, and this coil generally considered to be what? Generally considered as secondary. See, the two ends of the coil are connected to a galvanometer, and the other end of the galvanometer connected to the other end of the coil. See, when there is no flow of current in this coil of wire, there is no deflection available in this coil. That is, when the switch is open, there is no flow of electrical current. As there is no flow of electrical current, then there is no deflection in the galvanometer. But it was found out that when the switch S is on, when it is made to get switched on, then there will be a flow of current in the primary coil. When you are switching on, there is a momentary deflection in the galvanometer. But if the switch is kept on in the on condition for a long time, then there won't be any deflection in the galvanometer. At the time of switching on, you can able to get, there is a momentary deflection in the galvanometer. Similarly, when the switch is off, that is, you just take out the plug key. When the plug is taken out, that is, when the switch is made to get off, then also you can able to get a momentary deflection in the galvanometer, but in the opposite side direction that of the previous one. On பண்ணும்போது எந்த directionல இருக்கோ opposite side directionல இருக்கும். But continuously, if it is in switched on, switched off position, there won't be any deflection. So even though you are switching on, at the time of switching on, you will get a deflection. And if the switching on position is continuously like that, there won't be any deflection. Similarly, when you are switching off, at the time of switching off, you will be having a deflection in the opposite side direction, that of the previous one. And why this is thus so? Here there is no relative movement between the coil 1 and coil 2. But what you are able to get at the make or at the break of a nearby electrical circuit, you can able to get a momentary deflection in the neighboring coil. So that is the conclusion. So what do I have to do? See, whenever the switch in the or connected in the coil P is made to get on, then there will be a momentary deflection. Then there is a momentary deflection. Then there is a momentary deflection in the second coil or in the coil S. If the switch is in on condition, for a long time, then there is what? Then we can say, then there is no deflection in it. Then there is no deflection in it. But at the same time, if you are taking or if you are making the switch to be in off condition, then there will be a momentary deflection in opposite side direction. Similarly, let us write here. Similarly, when switched off, at that time, there is a momentary deflection. At that time, there is what? At that time, there is a momentary deflection in opposite side direction. So from this, what you can able to say? So from this experiment, it was concluded that at the make or at the break of an electrical circuit, make means switching on, break means switching off. So at the time of make or at the time of break, there is a momentary deflection in the galvanometer in opposite side directions. So what is the conclusion arrived? So the conclusion arrived is, we can say at the time of make or break of an nearby of an electric circuit, deflection is induced in the neighboring coil, in the galvanometer connected with the second coil. So connected with second coil. So this is the experiment. From this experiment, you can able to state a law, or you can able to state a definition of electromagnetic induction. Before stating that a definition for electromagnetic induction, I have to explain why this deflection is taking place. Now I have told you the experiment alone, the observation that you can able to get during that experiment. What is the observation? When the magnet is moving towards, a deflection is produced. When the magnet is taken away, the deflection is in the opposite side direction. Or reverse the magnet. Instead of north pole, if you are keeping the south pole, and if you are taking the magnet towards the coil, the deflection will be opposite to that, the previous case, as when you are bringing the north pole. When the magnet is moved away, then the deflection will be on the other side. Or keeping the magnet stationary, moving the coil towards or away, then also there will be a momentary deflection. Or we can able to increase the momentary deflection in the galvanometer by increasing the number of coils in the wire, or by increasing the speed of motion, or by increasing the strength of the magnetic dipole or magnet. This is one experiment. The next experiment is, see, whenever you have to consider two coils, a pair of coils, one is the primary coil and another one is the secondary coil. When you are passing the current through the primary coil by switching on, at the time of switch on, you can able to get a momentary deflection in the second coil, but the deflection will be momentary. If you go on switching on, or if you go on passing the current through the coil B, there won't be any deflection in the galvanometer. Similarly, at the time of break, when you are taking the key out, that is, the current that is flowing through the coil of wire gets stopped. Then also there is a momentary deflection, but in the opposite side direction to that of the previous case, but the deflection is considered to be momentary. So in the first experiment, it was said that as long as there is a relative motion in between the magnet and the coil, an EMF is induced or a current is induced, so a deflection is available in the galvanometer. From the second experiment, it was found out that at the make or at the break of a nearby electrical circuit, an EMF or current is induced in the other coil, which makes the galvanometer to get deflected. This was the conclusion of that experiment. See, let us see why this happens. So, why this deflection is taking place? Again, I am taking the diagram to explain that reason. See, when you are considering the first diagram, you take this first diagram. This is the first diagram. When you are considering this first diagram, you are having a coil of wire connected to the galvanometer, and nearer to that you are having the north pole of the magnet and the south pole of the magnet. When this magnet is available, around this you are having the magnetic field indicated by magnetic lines. When you are placing a nearby coil, this magnetic lines will be linked with this coil. When the magnetic lines are linked with this coil will have an magnetic flux. This coil will have an magnetic flux. This magnetic flux changes when the magnet is moved towards or when the magnet is moved away, or by turning the magnet, taking the south pole of the magnet towards or taking the south pole of the magnet away, or keeping the magnet stationary, moving the coil either towards or away. See, in all these performances, that is, in all these activities, what are the activities? By taking the magnet towards the coil, or by taking the magnet away from the coil, or by rotating the magnet and keeping the south pole nearer and taking the magnet towards the coil, or taking the magnets away from the coil, or keeping the magnet stationary, moving the coil either towards or away. In all these cases, or move both the coil as well as the magnet either towards or away. In all these activities, the magnetic flux that is linked with the coil due to the Bohr magnet changes. See, when you are bringing the magnet towards the coil, the magnetic flux increases. So the deflection is in one direction. But when you are moving, there is a change in magnetic flux. So a momentary deflection. When you are keeping it at rest, then there won't be any change in magnetic flux. Similarly, when you are taking the magnet away, then the magnetic flux decreases. So since it decreases, opposite to that of the increasing case, the deflection, momentary deflection, is in the other side. See, this is happening when the magnet is moving towards or away, or when the coil is moving towards or away, or when both magnets are moving towards or away. When magnet and the coil are moving towards each other, flux increases. When they are moving away, flux decreases. So from this, we can say, as long as there is a motion, means there will be a change in magnetic flux. Due to the change in magnetic flux, an EMF or an electrical current is induced in the coil of wire, which makes the galvanometer to get deflected. Hope you should have understood. This is from the first experiment. Let us consider the second experiment. See, in this case, there is no movement. Yeah, here we are having two coils of wire, coil 1 and coil 2, or coil P and coil S. Here we are having no movement between the two magnets, two coils P and S. How you can able to get the magnetic field, or how you can able to get the EMF or the current which produces the deflection in the galvanometer? Let us see. When you are switching on, the electrical current that is passing through the primary coil, the current I that passing through the primary coil increases from what? Increases from 0 to maximum. When you are switching off, it is 0. At the time of switching on, it increases from 0 to maximum. See, according to Ampere, at the initial position or the initial introduction of this lesson, I have told Oersted and Ampere. According to Ampere, it was being stated that around a current carrying loop of wire, a magnetic field is produced. That magnetic field induces or links some flux with this second coil. Whenever this current changes, then the magnetic field changes. When magnetic field changes, the magnetic flux changes. When magnetic flux changes, there is a current induced. That current is producing a deflection in the galvanometer. See, when I am switching on, the current increases from 0 to maximum. So flux increases. When flux increases, the deflection, the momentary deflection will be on one side. But when you are switching on, the current is constant. When the current is constant, magnetic field is constant. When magnetic field is constant, flux is constant. There is no change in flux. When there is no change in flux, no deflection or no current or no EMF is induced. Similarly, when you are switching off, when you switch off, what will happen? See, when you are taking the key out, when you are switching off, what will happen? When you are switching off, then the current changes from maximum to 0. So the magnetic field decreases due to decrease in current. When the magnetic field decreases, what happens? Then flux decreases. When flux decreases, EMF is induced, but in opposite side direction, because increase in one direction, decrease in another direction. So due to the change in direction, the momentary deflection will be on the other side. So at the make or at the break, you can able to get a momentary deflection in the galvanometer because of this cause. The cause is at the time of switching on, the current increases from what? The current increases from 0 to maximum, because of which the flux linked with the second coil increases from 0 to maximum, which produces a momentary deflection in the galvanometer, producing an induced current. Similarly, when you are considering when you are considering the switching off condition, the current decreases from maximum to 0. So the flux decreases. When there is a decrease in flux, an EMF is induced and the deflection is produced in the opposite side direction. Hope you should have understood this. So with this, what happens? The definition for electromagnetic induction is given by whom? The definition for electromagnetic induction is given by Faraday. So what is the definition for what? Definition for the electromagnetic induction. So it was being defined from the conclusion of the experiments, from the observation got from the experiments, how they are defining whenever, very important, whenever there is a change, in magnetic flux linked with the coil, or a conductor, linked with the coil or with a conductor, an EMF or EMF is induced, that EMF is called as induced EMF. Because of that EMF, a current is induced. The current induced. Similarly, we can write the current induced is known as, or is called as, we can write it out as induced current. This phenomenon is called as electromagnetic induction. So this is the definition for what? This is the definition for electromagnetic induction. So let us recall again. Whenever there is a change in magnetic flux linked with the coil or any conductor, then an EMF is, due to the change in magnetic flux, an EMF is induced in that coil or in that conductor. That EMF induced is called as induced EMF, and the current induced is called to be induced current. And this phenomenon is called as electromagnetic induction. See, if you want, you can also define it in the reverse way. See, we can write electromagnetic induction is defined as the phenomenon of inducing either electrical EMF or electrical current due to change in magnetic flux, in a coil or in a conductor, that we are taking or considering it as electromagnetic induction. Any difficulty? So this part we are calling it out as Faraday's experiments. From Faraday's experiments, we can able to define and statement or define a phenomenon called to be electromagnetic induction. See, from this concept of electromagnetic induction, Faraday can able to give out two laws called to be Faraday's laws of electromagnetic induction. That we shall see it in our next video, and hope you should have understood